All right, today we're going to put on our detective hats and solve a fascinating real world engineering mystery. And believe me, this isn't just some problem out of a textbook. This is the kind of stuff that matters for things like cryogenic pipelines or equipment on high altitude jets. We've got a victim, this supercooled pipe, and our main suspect, a high speed wind. Our job? Figure out exactly how much heat this wind is pumping into the pipe. Okay, let's dive in and crack this case. So here's the scene of the crime. You've got a 15-meter pipe, and it is chilled to an absolutely incredible minus 150 degrees Celsius. I mean, that is colder than any natural place on Earth. And just hammering this thing is a relentless 22-meter per second crosswind. That's almost 80 kilometers an hour. We are talking about a seriously extreme environment here. And that brings us to the central question of our whole investigation. Just how much heat, how much raw energy is that relatively warm air forcing into this freezing cold pipe every single second? That's the number we're here to find. And here's how we're going to get to the bottom of it. This is our roadmap. First, we'll lay out the problem. Then we're going to profile the air itself. After that, we'll figure out what the airflow is doing, tackle the master equation that ties it all together, and then finally, we'll calculate the total heat gain. A nice, clear, step-by-step investigation. Okay, first things first. Every good investigation has to start by just gathering the evidence, laying out all the known facts of the case. So here is what's in our case file. We know the pipe's diameter is 12 centimeters. We know it's 15 meters long, and its surface is a ridiculously cold negative 150 Celsius. The air around it, though, a pretty comfortable 25 degrees. And that wind is just blasting away at a steady 22 meters per second. These are our starting clues. Okay, so we've got the basic facts down. Now, we need to understand the medium where all this action is happening, the air. We've got to know its properties right at that point of contact, right where it meets the pipe. To do that, we need to understand a concept called film temperature. The best way to think of it is as the meeting point temperature. See, it's not the pipe's temperature, and it's not the air's ambient temperature way out there. It's the simple average of the two, right in that super thin layer or film of air that's touching the pipe. This is the temperature that really tells us how the air is going to behave. And you know what? Calculating it is super simple. We just add the two temperatures together, we divide by 2, and bam, we get minus 62.5 Celsius. Now, for all our engineering calculations, we've got to convert that to Kelvin, which gives us 210.65 K. See? Easy enough? So why did we even bother with that film temperature? Well, because it's the key that lets us look up the air's official record at that specific temperature. This gives us its thermal conductivity, how well it transfers heat, its kinematic viscosity, which is basically how goopy or resistant to flow it is, and its Prandtl number, which kind of compares how fast the flow's motion changes versus how fast its heat transfers. These are the crucial stats, the fingerprints we're going to need for our next step. All right, so we've profiled the air. Now we need to profile its movement. When that wind hits our pipe, is it flowing past in a nice, smooth, orderly way, or is it a chaotic, jumbled mess? To answer that, we use a powerful tool called the Reynolds number. Think of it like a personality test for fluid flow. A low Reynolds number, that's like a wide, lazy river, super smooth, what we call laminar flow. A high Reynolds number, oh, that's like crashing whitewater rapids, chaotic, unpredictable, turbulent flow. And here's the formula we use to find it. It's actually just a simple relationship between the wind's velocity, the pipe's diameter, and that kinematic viscosity we just looked up from our air profile. So when we plug in the numbers from our case file, we get this. 352,000. Whoa, yeah, that is a big number. So what does a big number like that actually tell us? Well, it means our flow is no gentle river. It's a raging torrent. The flow is highly turbulent. And that chaos, it is incredibly effective at transferring energy. In this situation, it's transferring a massive amount of heat to our pipe. This right here is a huge clue. So, discovering that turbulence is the key that unlocks this whole next phase of our investigation. It lets us pick our main tool for cracking this case, the Churchill-Bernstein correlation. Just think of it as the master equation. Okay, take a deep breath. Yes, I know, it looks intimidating. This equation is an absolute beast, but it's brilliant. It's designed to handle a huge range of conditions, including the exact kind of high turbulence scenario we've just found. But don't you worry, we're going to break it down piece by piece. Let's just start right here. This first big chunk of the equation is the foundation. It calculates the basic heat transfer using those Reynolds and Prandtl numbers we already have. This part gives us our baseline answer. But now look at this part. This second bracketed term is the really clever bit. It's a special correction. It's our turbulence factor. It takes our huge Reynolds number and uses it to fine-tune the result, specifically accounting for all that chaotic, high-energy turbulent flow. This is what makes this equation so powerful and accurate for our case. And after running all our data through that master equation, it spits out the next major piece of evidence we need, the Nusselt number. In our case, it comes out to roughly 504.5. And this number, this is the key to our final calculation. All right, this is it. We've gathered all our clues, the air properties, the flow characteristics, and now this Nusselt number. It's time to put them all together and solve this case once and for all. The final reveal is next. So how do we use that Nusselt number? First, we use it to find something called the heat transfer coefficient, or H. This number is crucial. It tells us exactly how good the heat is at moving from the air to the pipe's surface. For us, it's about 80. Then, we just calculate the total surface area of our pipe. And finally, we multiply that H value, the area, and the temperature difference between the warm air and the cold pipe. And that gives us the grand reveal, the answer to our mystery. The total rate of heat being absorbed by that freezing cold pipe is 79.05 kilowatts. That is a massive amount of energy being transferred every single second. Case closed. But just how massive is that number really? Well, let's compare. With our high wind, that turbulent convection is so powerful that it results in that 79 kilowatt heat gain. But what if the wind just died down to almost nothing? Then the heat would only transfer through gentle, natural conduction. The heat gain would absolutely plummet. It would be a tiny, tiny fraction of what we calculated. That wind, it's everything. Let's put this into perspective for a second. 79 kilowatts. That's the energy equivalent of taking more than 50 powerful 1,500-watt space heaters, turning them all on high, and pointing them at that one section of pipe. That is the incredible, invisible power of the wind in this scenario. Which, it kind of makes you wonder, right? What other invisible, high-stakes energy transfers are happening all around us every single day? Something to think about. Thanks for helping us crack the case.
Hey everyone, so today we are cracking the code on a problem that engineers deal with all the time. How in the world do you predict heat transfer when you're dealing with something as messy and chaotic as turbulent flow? Well, we're going to see how one single, really powerful equation can take all that chaos and boil it down to a predictable number.
You've definitely felt this before, right? You're outside, a gentle breeze feels nice, but then a strong gust of wind hits and suddenly you're shivering. But by how much, really? Is a 30-mile-an-hour wind just twice as cooling as a 15-mile-an-hour wind? Or is there something more going on? That is the exact question we're going to dig into.
And to get our answer, we're using this incredible tool called the Churchill-Bernstein correlation. Now, in engineering, a correlation is basically a practical, battle-tested formula that's built on a ton of real-world experimental data. It's kind of like the master key that lets us connect things like wind speed and fluid properties to get a super precise value for heat transfer. And this formula, it's going to be the engine for everything we do today.
Okay, so let's run the numbers. We're going to throw this formula at a hypothetical 20-centimeter process pipe, and we'll calculate its heat transfer coefficient at 3 completely different wind speeds, starting with our baseline.
Our first data point is a nice, steady wind of 15 meters per second. Think of this as our starting line. Let's see what the formula spits out.
So first up, we calculate the Reynolds number. Just think of it as a score for how chaotic the airflow is. At 150,000, the flow isn't perfectly smooth, but it's not totally wild and turbulent yet either. We plug that number into our big correlation to find the Nusselt number, which basically tells us how much better cooling with airflow is compared to just letting something sit there. From that, we can finally solve for our main target, H, the heat transfer coefficient.
And boom, here is our first result, 49.0. Okay, that's our baseline. Now, let's see what happens when we really crank up the speed.
All right, let's kick things up a notch. We're bumping the wind speed to 25 meters per second. Any guesses on what's going to happen to our number? We run it through the exact same process. And right away, notice the Reynolds number just jumped to 250,000. That pushes our Nusselt number way up from around 338 to nearly 488. So, what does that do to our final answer?
The heat transfer coefficient leaps to 70.7. Okay, now this is getting interesting. We increased the speed by about 67%, but the cooling effect jumped by 45%. So this is definitely not a simple one-to-one relationship. Something more powerful is at play here.
And for our last test, we are tripling our original speed. We're cranking it all the way up to 45 meters per second. This is where things should get really wild. And just as we thought, our Reynolds number shoots way up to 450,000. We are deep in turbulent territory now. And look at that Nusselt number. It's more than doubled from where we started. The math is definitely showing us a massive effect.
And there's our final number, 120.6. Whoa, that is nearly 2.5 times our starting value. And that is the key takeaway. Tripling the wind speed didn't just triple the cooling effect, it amplified it like crazy.
Okay, let's just look at all three results together. This table tells the whole story, doesn't it? As the velocity and that Reynolds number go up, the heat transfer coefficient just skyrockets. This is the power of turbulent flow in action. But, this kind of brings up a question. When exactly does that crazy powerful turbulence really kick in?
So there's clearly a tipping point. There's a specific moment where the airflow just stops being smooth and orderly, and instead it erupts into this chaotic, swirling state we call turbulence that just so radically improves how heat gets transferred. So get this, the Churchill-Bernstein correlation actually has a trigger for this transition built right into it, a very specific Reynolds number where it starts accounting for the onset of major turbulence. So at what exact speed do we hit that magic number?
The answer is 28.2 meters per second. Now, why that specific speed? Because at that velocity, the Reynolds number crosses a critical threshold of 282,000. And that's the point where, according to this formula, the physics of the flow just fundamentally changes, and the really powerful effects of turbulence take over. So, just how much of a difference does this turbulence actually make? Well, for our final step, we're going to dive right into the equation itself and isolate the exact term that accounts for this effect. We're going to actually quantify its contribution.
So to do this, we're going to look at a velocity that's 1.5 times our threshold speed. That gives us a Reynolds number of 423,000. Then we take just this little bracketed part from the bigger equation. This is the secret sauce for turbulence, and we solve just for that.
And the result is 1.95. This one number, it quantifies the entire amplification effect of turbulence in our specific scenario. It's literally telling us that the chaotic mixing of turbulent air is nearly doubling the heat transfer compared to what a smoother, less chaotic flow would do. It's a perfect numerical snapshot of chaos at work.
And this really gets to the heart of it all. That factor of 1.95 isn't just some random number. It's the physics of turbulence quantified. That chaotic mixing of air just whisks heat away from the surface so much more effectively than a smooth, or as it's called, laminar flow, ever could.
So why do we go through all this trouble just to crack the code of a hot pipe in the wind? Well, because this isn't just about one pipe. This exact principle is absolutely fundamental to modern engineering.
I mean, understanding this nonlinear relationship is totally critical for designing everything from the tiny cooling fins on your computer's processor to the massive heat exchangers in power plants and even the safety systems in nuclear reactors. By turning turbulence from this big unknown into a predictable factor, we can manage energy, we can ensure safety, and we can build way more efficient technology.
And that kind of leaves us with the final thought. The Churchill-Bernstein correlation takes something as wild and unpredictable as turbulence and turns it into a reliable, predictable number. It really makes you wonder, if we can model this kind of invisible chaos with such elegance, what other complex forces in our universe are we just one equation away from truly understanding?
Today, we're diving into one of the most critical challenges in all of engineering: how to keep a nuclear reactor from, well, melting down. This is a problem where the stakes couldn't be higher, and getting the math exactly right is everything. All right, let's get right into it.
So, here's the central question we're tackling. How in the world do you cool a super hot reactor rod using liquid sodium? I mean, this isn't like cooling your car engine with a bit of water and antifreeze. We are talking about some seriously extreme temperatures and some pretty exotic materials.
You know what? Let's treat this like a detective case that we need to crack. And the first rule of any investigation is you have to gather the facts. We need to understand the scene of the problem.
Okay, here's our case file. We've got a rod, just 15 millimeters wide.
that's scorching hot at 450 degrees Celsius, and it's being cooled by liquid sodium that's flowing past it at 2.5 meters per second. Now, pay really close attention to these last two numbers. They're the crucial clues. The thermal conductivity, K, is super high, which tells us sodium is great at conducting heat. And the Prandtl number, PR, is incredibly low at just 0.011. Remember that one. It is the secret key to this entire problem.
So, we have our parameters, all our facts laid out. Now, every good detective needs the right tool for the job. And in the world of heat transfer, that means finding the right formula to model the physics.
Our tool of choice? It's a real heavy hitter called the Churchill-Bernstein correlation. This thing is a powerful and, widely used equation that's specifically built to figure out how much heat moves from a cylinder, like our reactor rod, into a fluid flowing right past it. It might look a little complicated, but it's designed to be tough and work across a huge range of conditions.
But hang on a second. Here's the catch. Can we just plug our numbers into this fancy formula and trust what it spits out? I mean, liquid sodium is not water. It's not air. It behaves in really strange ways. We have to be absolutely sure that our tool is even the right one for this extreme scenario.
So before we can even think about solving the case, we have to run a critical diagnostic. It's called the Pectelet number test, and it's basically going to give us a big thumbs up or thumbs down on whether we can proceed. Luckily, this validation is a pretty straightforward three-step process. First, we'll calculate something called the Reynolds number to get a feel for the fluid's flow. Is it nice and smooth or totally chaotic? Then, we use that to find the Pectelet number. And finally, we just check if that number is above a certain line in the sand. Simple as that.
And boom, step one is done. After we run the numbers, that's the velocity times the rod diameter divided by the viscosity, we get a Reynolds number of 83,333. A number that high tells us one thing for sure. The flow of this liquid sodium is highly turbulent. It's chaotic, which honestly is exactly what you'd expect in a situation like this.
All right, now for the real test. The Pectelet number is surprisingly simple to calculate. It's just the Reynolds number we just found, multiplied by that tiny little Prandtl number from our case file. So we take 83,333 and multiply it by 0.011, and we get 916.6. Now, the rule for using our Churchill-Bernstein formula is that this number has to be greater than 0.2.
And there you have it. 916.6 is not just bigger than 0.2. It absolutely blows it out of the water. This is our confirmation. Our tool, the Churchill-Bernstein correlation, is 100% valid for this case. We have the green light.
Okay, our tool has been validated. We're good to go. It is time to crack this case wide open.
So we take all the numbers from our case file and we carefully plug them into the Churchill-Bernstein formula. And what it gives us isn't actually our final answer. Instead, it gives us a really important intermediary value, a kind of special dimensionless number that acts as a bridge to get us where we need to go. And that number is called the Nusselt number. For our specific conditions, the temperatures, the speeds, the fluid, the calculation gives us a Nusselt number of 51.5. This right here, this is the key that's going to unlock our final answer.
So what do we do with this kind of abstract number? Well, the Nusselt number is the key that unlocks the one practical value every engineer desperately needs here. And that value is H, the convective heat transfer coefficient. The best way to think about H is as a performance rating. It tells us exactly how aggressively heat is ripped away from the rod's surface and into that liquid sodium. And here it is, the answer we've been working towards. The heat transfer coefficient H is a staggering 257,500 watts per meter squared Kelvin. Now, to give you some perspective, if you are trying to cool this rod with just air flowing past it, your H value might be around 100. This number is thousands of times higher. It proves that liquid sodium is an unbelievably effective coolant.
So we've got our number. Case closed, right? Not so fast. The most important part of any of these problems is understanding the why. Why is this number so ridiculously huge? What's the secret that's hidden inside the physics?
Yeah, let's dig a little deeper here. What is it about liquid sodium that makes it so wildly different from something we're all familiar with, like water? Well, the answer was actually hiding in plain sight, in that tiny little number we saw right at the beginning of our case file. It all comes down to the Prandtl number. The best way to think about it is like this. Imagine you're standing by a stream. You drop in a blob of blue dye, and at the same time, you pour in a little bit of hot water. The dye spreading out shows you how the flow itself mixes things up. That's momentum diffusion.
The heat spreading out shows you thermal diffusion. The Prandtl number is simply the ratio of those two speeds. Now, in water, the Prandtl number is high. That means the dye, the momentum, spreads way faster than the heat does. The heat kind of just gets carried along for the ride by the currents. But in liquid sodium, it's the complete opposite. Heat diffuses at lightning speed, zipping through the metal way faster than the fluid itself is even flowing.
And that is why liquid metals have a Prandtl number that's practically zero. They are just incredible at conducting heat. For our problem, that number was a tiny 0.011, which just confirms that for liquid sodium, heat conduction is the absolute dominant way energy moves around.
So here's the crucial aha moment. Why is the Churchill-Bernstein formula so much better? Because it was built for this. Deep inside the formula, there's a special term that has the Prandtl number, PR, in the denominator. And as you know from math class, when you divide by a super tiny number, the result gets massive. This term correctly adjusts the entire equation for the bizarre physics of liquid metals. Simpler formulas, they don't have this term, and they would give you a dangerously wrong answer.
And that really is the big takeaway here. The right tool, the right equation, it doesn't just spit out a number for you. It's a model of reality. And when you use it correctly, it actually reveals the hidden physical principles that are secretly governing the world all around us.
It really makes you wonder, doesn't it? We just used a mathematical formula to safely understand and control the immense power locked inside a nuclear reactor. What other invisible, powerful forces, whether it's in physics or finance or even biology, are just out there, waiting for the right mathematical tool to come along and help us understand and control them?
All right, today we're going to solve a real-world engineering mystery. We're going to figure out exactly how much heat is just pouring out of a single pipe in a chemical plant. We'll walk through the actual calculations engineers use, and you'll see how a few key numbers can mean the difference between an efficient system and a really dangerous one. Okay, so we're going to flip the script a bit here. Instead of starting with the problem, we're going to start with the answer, the final result. It's a single, powerful number that honestly tells a whole story. Boom, there it is, 25,928 watts. That is the amount of heat energy blasting out of this one section of pipe every single second. It's a huge number, right? But what does that even feel like? To really wrap your head around that, picture this. It's the same energy as running about 25 kitchen microwaves on full power all at once, all day long. That is a staggering amount of wasted energy. And it's a perfect example of the kind of problem engineers have to wrangle with every single day. So, where in the world does a number like that come from? And, what's the big deal? To answer those questions, we've got to dig into the problem itself. All right, let's paint a picture. We're on site at an ethylene glycol plant, a pretty common type of chemical facility. And our focus is on just one piece of equipment. Okay, here are the vitals, the clues, if you will. We've got a 10-meter pipe. Inside, it's carrying super hot ethylene glycol at 150 degrees Celsius. The air outside is a chilly 10 degrees, and there's a pretty strong wind, 15 meters per second, blowing right across it. These are our knowns. So the big question is, with all that going on, how much heat is just pouring out of this thing? Right, so engineers don't just, eyeball this stuff. There's a method to the madness. A really precise 4-step process to get from those raw conditions to our final number. It's a journey from wind on a pipe to total energy loss. Here's the game plan. First up, we've got to figure out what the airflow is doing. Then we'll see how good that air is at yanking heat away. Next, we calculate the specific rate of that transfer. And finally, we scale it all up to get the total heat loss. So let's jump into step 1. First up is something called the Reynolds number. Now, don't worry about the name. All it does is tell us one thing. Is the air flowing in a nice, smooth, orderly way? That's called laminar flow. Or is it a chaotic, swirling mess, which is turbulent? And trust me, that distinction is everything when it comes to transferring heat. So we run the numbers and we get 71,428. Now, to give you some perspective, anything over about 4,000 for this setup is considered turbulent. We're at over 71,000. So yeah, the air around this pipe is basically a chaotic whirlwind. And that is our first big clue. Okay, next piece of the puzzle, the Nusselt number. This one tells us how the heat is escaping. Think of it like this. Is the heat just kind of warming up the layer of air right next to the pipe? That's conduction. Or is the wind literally grabbing the heat and carrying it away? That's convection. The Nusselt number tells us which one is winning. And for our pipe, we get a Nusselt number of around 198.5. That is a huge number, and it screams one thing. Convection is totally dominating. That chaotic, turbulent wind we found, it's doing an absolutely incredible job of stripping heat off that pipe. All right, now we get to the big one, the heat transfer coefficient, which engineers just call H. This is where it all comes together. It takes the personality of the flow from the Reynolds number and the effectiveness from the Nusselt number, and it mashes it all up with the physical properties of the air itself. It basically turns all that physics into one single, super useful value. And that value is 58.95. So what does that mean? It means for every single square meter of the pipe's surface and for every single degree of temperature difference, 58.95 watts of energy are just gone, escaping. We finally have our rate. Now we can solve the whole mystery. But hold on. Just when you think we've nailed it, there's a plot twist. Because, the real world is messy. The formulas and correlations engineers rely on, they're amazing, but they're not perfect. They always have a little bit of wiggle room. In fact, the source material for this problem tells us point blank, this specific formula has an uncertainty of plus or minus 20%. And for an engineer, that is not a footnote. That is a headline. So what does that actually mean? It means our answer, that 25,928 watts, is really just the most likely number in a whole range of possibilities. The real heat loss could be as low as about 20,700 watts, or it could be as high as 31,100. And when you're designing a system to handle that, you can't just plan for the middle. You have to be ready for the worst-case scenario. Okay, we've cracked the case of the overheating pipe. We know how much heat it's losing, and we even know the uncertainty. But now, let's put on a different hat. Let's switch from being detectives to being designers. What if, for some crazy reason, we actually needed to double the amount of heat coming off that pipe? So here's the challenge. The only thing we can change is the wind speed. To double the heat transfer, you just double the wind from 15 to 30 meters per second, right? Simple. Well, not quite. See, this is one of those things where physics gets a little tricky. The relationship between wind speed and heat transfer isn't a straight line. It's not a one-to-one thing. It's actually proportional to the velocity raised to a power, which means to get double the result, you need to do way more than double the input. And the answer turns out to be around 52 meters per second. Think about that. Not 30, 52. That's nearly 3.5 times the original wind speed just to get double the effect. It's a perfect example of how these nonlinear effects can really surprise you if you're not paying attention. So let's zoom out. We've seen how a single number can tell a massive story. We've walked through how engineers systematically break down a complex problem. And we've seen how they have to grapple with the messy realities of uncertainty and these kind of weird nonlinear effects. But it leaves us with a bigger question, right? In a world built on these super precise calculations, how do we design things that can handle the unexpected? That is the real challenge. Today, we're going to tackle a classic engineering puzzle, one that's happening all around us, but you probably never even notice it. We're going to figure out exactly how much energy is just silently escaping from a rack of hot industrial pipes. And trust me, the final number might just blow your mind. So this is the big question, right? On the surface, it seems pretty straightforward. But we're going to calculate the exact amount of energy that is literally just bleeding away into the atmosphere from what looks like a totally normal piece of equipment. All right, first things first, let's set the scene. Like any good detective, we've got to gather all the facts of the case before we can solve it. So what exactly are we dealing with here? Okay, here's our setup. We've got a rack with 5 pipes all running parallel to each other. Each one has a diameter of 10 centimeters and is 20 meters long. Now, these pipes are hot. We're talking a surface temperature of 180 degrees Celsius. Meanwhile, the air around them is a pretty standard 30 degrees. And to make things interesting, there's a wind blowing across them at 12 meters per second. These are our clues. And here is our mission, should we choose to accept it. We're not just looking for the rate of heat loss, like how much is lost per second. No, we are hunting for the grand total, the full amount of energy in megajoules that this entire setup wastes over one full 24-hour day. That's the number we're after. Now, to solve a big problem like this, we have to start small. Trying to analyze all 5 pipes at once would just get way too complicated. So our strategy here is to zoom way in and do a little forensic analysis on just one single pipe. If we can understand one, we can understand them all. our very first step is to figure out something called the film temperature. Just think of it as the average temperature in that super thin layer or film of air that's right up against the pipe's surface. So why do we care? Well, because the properties of air, like its stickiness or viscosity, and how well it conducts heat, they all change with temperature. We have to use the properties at this specific temperature to make sure our calculations are actually accurate. And here it is. All we have to do is average the pipe's surface temp of 180 degrees and the air's temp of 30 degrees, and we get a film temperature of 105 Celsius. This is our magic number. This is what we'll use to look up all the important air properties for our next few steps. Next up is the Reynolds number. Now, this is a brilliant little tool that engineers use. It's a dimensionless number, meaning it has no units, that helps us predict how a fluid is going to behave. In our case, that fluid is air. So is the air flowing smoothly past the pipe in nice, neat layers? We call that laminar flow. Or is it all chaotic and messy, full of swirls and eddies? That's turbulent flow. And believe me, the answer makes a huge difference for heat transfer. And we find it using this simple formula. We're basically just plugging in the numbers we know: the air's speed, the pipe's diameter, and the air's kinematic viscosity, which, remember, we figured out using that 105-degree film temperature. And the result is a Reynolds number of 50,420. Now, this isn't just a random number. It's a critical piece of the puzzle, because a number that high tells us the airflow is definitely not smooth. It is turbulent, and that chaotic, turbulent flow is way, way more effective at stripping heat away from a surface. So we know the flow is turbulent, but how do we actually quantify that? How much better is it at transferring heat? For that, we need the Nusselt number. To put it simply, it's a ratio. It compares the heat transfer from the moving air, that's convection, to the heat transfer you'd get if the air were perfectly still, that's conduction. The bigger the Nusselt number, the more convection is winning the battle. Now, we don't just guess this number. It's calculated using a very well-established engineering equation called the Churchill-Bernstein correlation. It's this powerful tool designed for this exact situation, fluid flowing over a cylinder, and it uses that Reynolds number we just found. After plugging in our values, we get a Nusselt number of 145, and that confirms what we suspected. Convection is absolutely the star of the show here, just aggressively pulling heat off that pipe. We are just one step away from the one value we really need for this whole single pipe analysis. And that final piece is the heat transfer coefficient, usually shown as the letter H. This is the big one. This is what we've been working towards. It basically bundles up everything we just calculated, the air properties, the speed, the turbulence, all into one single number that tells us exactly how many watts of heat are flying off each square meter of the pipe for every degree of temperature difference. And all that work leads us right here to a heat transfer coefficient of 46.4. That's the key we've been looking for this whole time. We have officially cracked the code for a single pipe. Now, we can finally zoom back out and solve the whole problem. Okay, we are in the home stretch. We did the deep dive. We have all the info we need from our single pipe analysis. So now, it's time to scale up our findings and calculate the final energy bill for the entire 5-pipe rack. And you know what? The path from here to the final answer is actually beautifully simple. First, we're going to use our H value to calculate the heat loss rate for one pipe. Second, we'll multiply that by 5 for all 5 pipes. And finally, we'll convert that rate into a total energy amount over 24 hours. Let's do it. Okay, so using our heat transfer coefficient, the pipe's surface area, and the temperature difference, we find that just one of these pipes is losing heat at a rate of 43,730 watts. To put that in perspective, that is like running more than 40 high-powered microwave ovens all at once, 24/7, just from one pipe. Now, let's multiply that by 5. The entire rack is losing heat at a rate of 218,650 watts. That is over 0.2 megawatts of power, just constantly pouring into the air. You can see how what started as a simple pipe problem has scaled up into a really significant energy loss. And now for the grand finale, the answer to our original question. Over a 24-hour period, that constant heat loss adds up to a staggering 18,835 megajoules of wasted energy. We did it. That is the total energy bill for our hot pipe problem. So what's the big takeaway here? It's just how quickly these numbers can escalate. A totally common industrial setup, something you could walk past every single day without a second thought, can be a massive, invisible drain of energy, day in and day out. And that leaves us with one last really important question to think about. We just calculated the loss for 5 pipes. Now imagine an entire facility, a whole factory, filled with hundreds or even thousands of meters of pipes just like these. It really makes you wonder, doesn't it? What kind of insane energy savings are just sitting there, waiting to be unlocked with something as simple as better insulation? Definitely something to think about.